So group 1, Alisa, Darren, and Gracia will present about second project as well, thermal regulation in an active temperature sensor. So please turn on your videos and start whenever you are ready. Where is the other members of group? Alicia and Gracia. Okay, yeah, there they are.
Okay, so good afternoon, Sir Dedi, Kadevita, and friend. Today we are from Group 1 are going to present our first milestone of our project, which is the thermal regulation in an active temperature sensor, and we use op-amp as the comparator. This is the equipment that we use. We'll use PCB, thermistor, op-amp, resistor, and the other things. So how does it work? So first, the Ntc 20K thermistor will sense the temperature and it will set the value of the resistance. And then after that, if the temperature is lower than 38 degree, there will be no voltage that got outputted. And if the temperature is higher than 38 degrees Celsius, which basically means you have a fever, the op-amp will output voltage and it will turn on and will set the Arduino onto, and the Arduino will then set the LED to light.
Okay, so this one is the Ntc Thermistor, and basically an Ntc Thermistor that we use, it means that as temperature increases, the resistance will decrease. Okay, next. And we will be using an LM741 op-amp. And basically the important thing here is that we seek like the supply voltage, like the maximum, which is around 18 volts. And for our project, because we are within the range of -55 to 125, so we decided to use this LM741 op-amp. Okay, next. Okay, so this is basically the circuit that we thought of about the temperature sensing. So basically in multisim, we don't have a thermistor, and so we decided to model it with a resistor. So basically how an op-amp works is that the input voltage, the difference between the input voltage will be amplified by the operational amplifier. And basically, if there's a difference, it means due to the high gain of the amplifier, it will amplify a voltage. Now, if V plus, which is connected to this one, is higher than the V minus, then the op-amp will produce an output. However, if V plus is less than the V minus, the op-amp will not produce an output. And basically, this resistance value we chose through trial and error of calculation because we want to make sure that at normal temperature, it does not produce an output. So at how we determine the resistance value for the thermistor can be seen in the next slide. So this one, we have like a 20K thermistor NTC output table. And basically, we want to see the normal body temperature and the fever temperature. And so if it is normal body temperature, it is, you can see that it is around 12K. And so we model it as 12K in the multisim. And for the next one, for the fever temperature, if it is higher than that, it is around 11K ohm. Okay.
Okay, so this is the circuit when the thermistor resistor is set to 12 kilo ohm, which means that it's in a normal body temperature. So when we applied the voltage divider formula to this, we get that V plus is less than V minus. Therefore, there is no voltage output, so it would just be off. Next. This is when the thermistor resistor is set to 11 kilo ohm, which means it's in a high body temperature. And calculating again, we get the V plus is bigger than V minus. Therefore, there will be a voltage output, which means that it will activate the Arduino.
Okay, so for now, we haven't finished with the Arduino program, but basically later what we plan to do is that we will make the Arduino read the temperature as the thermistor increase or decrease, the temperature in the thermistor increase or decrease, and through the Steinhart-Hart equation shown here. And of course, later we will try to construct the the breadboard circuit. And yeah, I guess that's it for now.
Thank you, sir.
Okay, would like to ask group 6, Jesse and Hanif, to ask questions to group 1. Please turn on the video, Jesse and Hanif, and ask questions.
Hello, can you hear me?
Yes, we can hear you.
Okay. I have a question. Where are you going to plan to place the Arduino?
We're planning to place it next to the VPR3 over here in the output area.
Oh, why over there?
Because that part is where the op-amp will produce an output, and so we can try to relay the output. We also plan to use like a relay circuit, and later we will connect it to the Arduino, and basically it will turn on or off.
Oh, okay. Okay, that's quite clear. Okay, thank you.
Thank you, Jesse. Hanif, one last question.
Maybe why do you use 20K Ntc Thermistor?
Okay, because for the 20K thermistor, actually we tried also with 10K thermistor through the calculation. However, because we want to find like a small range of temperature, the 10K one gives a small range of resistance at that temperature. And so we try to use 20K. We can see that from 36 Celsius to 38, it decreased from 12K to 11K. But then for the 10K thermistor, the drop in resistance is very low, and so there's not much difference, and so it's hard to get an output using a 10K thermistor.
Okay, thank you.
Okay, Kak Evita, maybe some questions.
Well, actually, I don't have a question, but maybe you can directly ask or give comment for this group. It's like the previous one.
Group 1, this is the same. This is not active temperature sensing. Do you understand why it is not a active temperature sensing, what you just presented?
Yeah, because we don't control the current.
Yeah,
there's no
exactly. So this is too simple for you. I know 3 of you are smart. You should do more challenges, more challenging project, not just like this. Do you understand how to make it as an active temperature sensing?
We will try to use a heater later.
Yeah. If you don't understand, you can
yeah.
ask Martin. Martin already understood. Yeah, so active temperature sensing does not detect the temperature passively like now you're using thermistor, right? So thermistor is just based on the material properties, NTC or PTC. Then you try to convert that resistance change into voltage change. You can either use voltage divider or Wheatstone bridge. But that is just to display. Then the function of the Arduino is just to display the temperature. What I want is you use like the project, the project title, in the Google Classroom is thermal regulation in an active temperature sensor. Thermal regulation, that is the keyword. To regulate the thermal, it means you have to use a heater. Yeah, you have to use the heater. A heater that will flow current through it such that it has a certain temperature. Then when it is touched by something, let's say by your hand or by anything else, temperature will change, of course, and then that will cause the conductivity to change, the resistivity to change. And due to that resistivity change, the current will also change. The current flowing through it, or the voltage, depending whichever you want to measure, will change as well. And the function of your Arduino is to control, to regulate, such that then it will have the same current again, or same voltage again, whatever. And the amount of that change of current, adjustment current or adjustment voltage, will represent the temperature that it detects. In this case, it will be the hand that touched that heater. Do you get it, or do you not get it? Do you understand it or not?
Understand, sir.
Understand, eh? It's in the video also. Although, yeah, at that time I may not that well in explaining the concept, but there is a concept. So it is not a passive temperature sensing. Why we need an active temperature sensing? The idea is, with that control mechanism, then hopefully it should be more maybe precise or sensitive or accurate, yeah, compared to passive, like what you presented now. With passive sensing, you really depend on the material characteristic of the thermistor. Okay, and you need to calibrate it first, etc., etc. So for non-accurate measurement, yeah, it may be okay, but for accurate measurement or precise measurement, not that good. That's why the idea of what if you use active temperature sensing detection. Yeah, the drawback, the shortcoming is that you require energy, more energy for that detection, because you need to flow current or to flow voltage into that heater. Okay, got it? By the way, I think you could model actually thermistor in multisim, but not by using the resistor. You can use potentiometer instead. Yeah, potentiometer is variable resistor, whose resistance change is then determined by a certain equation. I'm not sure if in multisim you could also input that equation, that with the parameter T, temperature, for example. That is just another topic, because many of you try to model in multisim and use just a conventional resistor. I think modeling it using potentiometer will be more close to reality rather than conventional resistor. Okay, group 1, thank you very much. That will be all for you. Thank you. And I will call the next presenting group, which is group 6, Desi and Hanif. Yeah. Desi and Hanif. Okay, please turn on the videos. Okay, and share your screen.
Okay.
We can start now, right, sir?
Wait a moment. Yes, you may start as you are ready.
Okay. Good morning, Pak Dedi, Kak Dev, and everyone. Today, me and Hanif are going to present about our final project, which is the thermal regulation in the PCR chamber. So, the table of contents of our presentation. So, there is the introduction, primary steps of PCR, proposed solution, components, circuit, and schematic. Okay, the beginnings. So, a slight introduction about PCR. Well, as you guys all know, nowadays COVID has spread all around the world, and also has already given us a big impact, a huge impact to the world. Since then, scientists have researched about this virus, and so far until now, PCR is one of the most accurate methods of detecting for the presence of corona.
Okay, so PCR involve three primary steps. The first one is denaturing stage, the second one is the annealing stage, and the third one is extending stage. In denaturing stage, for instance, the double-stranded DNA that is obtained from human, it is separated into two single stranded DNA, and it requires 94 until 95 degrees Celsius. While the annealing stage requires 50 until 56 degrees Celsius, so we lower the temperature. And then in this stage, the primer, a specific primer, would bind into that target sequence of single-stranded DNA. And then we again increase the temperature into 72 degrees Celsius. In this case, it is extending stage. So the primers are extended and it synthesizes more stranded DNA. So each of these stages require different durations. For the denaturing stage, it requires 20 until 30 seconds and 20 until 40 seconds for the annealing stage and 20 until 60 seconds for the extending stage. So this is so challenging because we have to maintain the range of temperature on a specific range of temperature. Like for instance, otherwise, if we have a higher temperature or a lower temperature than the ideal temperature, for instance, in the annealing stage, the primer would not bind perfectly to the single-stranded DNA. So our proposed solution is by building a thermal cycling system, and we're gonna use a microcontroller called Arduino Uno, and it is function to control all the components in the systems to control the temperature of the sample. And because we our only focus here is only the electrical part, so we're gonna use a sample in the form of water.
Components. So the four main components for our device here are shown here: a heater, cooler, temperature sensor, and Arduino. Okay, heater. So to get getting deeper to our components, the heater that we're going to use is the nichrome wire. Nichrome wire is a non-magnetic alloy of chromium and nickel. So this substance is actually commonly used as a heating element. The advantage of using this nichrome wire is that it is low on cost and it's actually relatively stable in high temperatures. And to make it to improve its performance, we form it into a meander shape, like this kind of shape. It will be shown in the next slide. Okay, a cooler. So for the cooler, we're going to use three different components, which are the Peltier cooler, the heat sink, and the cooling band. Peltier cooler. Peltier cooler is a thermoelectric cooler, or TEC, which uses the Peltier effect. Uh, it's like an active heat pump. So like it transfers heat from another side of the Peltier cooler to the other side. So in the end, one side will be hot and one side will be cold. So like it's like an active heat pump. Heatsink. Heatsink is like it's a component that provides a surface area for heat flow from hot components to flow away from the hot component. Similar as cooling fan, it improves the performance of hot components. So for the cooling band, yeah, similar to the heat sink, it also improves the performance of hot components such as Peltier cooler. It improves by blowing cool air to the hot components. Temperature sensor. Okay. For the temperature sensor, we're going to use thermistor. Thermistor is a device that is used in a circuit to measure temperature. Um, sorry. Uh, the advantage of using thermistor is that thermistor is actually very sensitive. A slight change in temperature will be detected by the thermistor. The advantage of using thermistor is that it's not expensive also, and they provide fast response. And there, the type of thermistor that we will use for our device is the Ntc Thermistor, uh, because the Ntc Thermistor reduce if the temperature increases, the resistance of the probe of the thermistor decreases. That's why we use Ntc. And in detail, we're going to use the LM35 model thermistor. Why? Because the LM35 model has the accuracy ranges accuracy from 0.5 degrees Celsius to 1 degree Celsius. And it's suitable for around minus 55 degrees Celsius to 150 degrees Celsius. Miscellaneous. Okay, for this, these are some other components that we use in our circuit, which are the relay, the 4-channel relay, the resistor, and adapter, 12-volt adapter.
Okay, now we're going to talk about the outline of the circuit. So basically either 12-volt battery or adapter AC to DC converter. It is going to be connected to the relay. And because we have 4-channel relay, which are then connected to the 4 elements here, um, we're going to connect this power supply, the battery, in parallel so that each channel will obtain 12 volts. And then it is connected to the Arduino Uno, the input, digital input in the Arduino Uno, so that the Arduino can detect all these 4 components and then control whether we have to turn on the heater or turn off the heater or turn on the cooler or something else. And then we also connect the thermistor into the Arduino Uno so that we can read the temperature. However, Arduino cannot just directly read the temperature, so that we have to convert the resistance of the thermistor first into the temperature, readable temperature, using a specific equation, Steinhart equation. And then the Arduino itself, it's going to be connected with the computer. And for the schematic, we've actually had made design in the Tinkercad. So this is the heating element. This is the nichrome wire, and it is separated with the conductor. And underneath, this is the cooling element. So as you can see, the white square here, it is the Peltier cooler, and it is connected attached to heat sinks. And on the bottom, we have this cooling van. So it will blow air to the hot side of the Peltier cooler. And this is just a rough sketch. This is optional if you want to make a casing or not. These heating and cooling elements will be included inside the casing. And then on top of the heater, we're gonna add the sample of the water sample. And then in this area, we're gonna make a partition to include the circuit, the Arduino and stuff. And we're also gonna connect the thermistor into the heating element so that we can keep track of the temperature of the heating, whether it is more than the ideal temperature or lower than the ideal temperature, so that we can keep track and program it in the Arduino. And for the sake of air regulations of the casing, we make one side of it some holes in order to air going through the casing. And then this fan right here on the other side, it sucks out all the heat inside the system and out of the outer system. Yeah, so basically that's it. Thank you very much.
Okay, thank you, Jesse and Hanif. It is still well on time. Very impressive presentation from my point of view, yeah, although I have later some points to comment. I would like to ask Group 1, Alicia, Darren, and Gracia to ask questions to Jesse and Hanif. Alicia, Darren, Gracia, please turn on the videos and ask questions to the presenting group. Please unmute yourself and ask the question.
Okay, I will ask first question. Earlier you said that you will use nichrome wire for heater material. Can I ask, is there a better material that can be used to make the heater?
Yeah, actually there are a lot. We have basically have several options using nickel wire and also aluminum wire. But we end up using nichrome wire because we have reviewed some previous studies that also use the nichrome wire. And it is also a good conducting materials for the heater, as said by Jesse earlier.
Okay, thank you.
Other questions from group 1?
I have a question.
Yes, Alisa.
For each of the components, how much voltages is required for them?
Oh, for each, yeah. Maybe you can show the components list, maybe from the flowchart to flowchart. So for the nichrome wire, the Peltier Cooler fan, and the other fans, they're going to use 12 volts. Yeah, they need 12 volt to operate. And for the Arduino, it will for the thermistor, it will get 5 volt from the Arduino, and the Arduino will get 5 volt from the computer, because the Arduino will be the computer will be plugged to the Arduino using a USB plug.
Does it answer your question, Alisa?
Yes, it does.
Okay. Other questions maybe from group 1? Darren?
How can you tell how to know whether the hot side or the cold side of the Peltier cooler, and how will you place it on the design?
Oh, sorry. Well, basically, the top side of the Peltier cooler is the cold side, and the bottom part is the hot side. And in order to, when in doubt, when we don't really doubt about determining which hot side or cold side, you can just plug in the Peltier cooler, but just for a few milliseconds, because Peltier cooler is very sensitive to temperature change. So you just have to plug it and then unplug it too, and then test it with your hands, whether it is the hot side or the cold side. And yeah, it is going to be connected to the Peltier cooler. The cold side, it is going to be connected to the upper part of the heating elements. So the hot side will be blown by the fan on the bottom part, as in the schematics.
Okay, thank you. Kak Devita, maybe one short question. Please unmute yourself, Kak Devita.
Oh yeah. Okay, can you please move to the slide that Tinkercad slides, the Tinkercad that shows the design of your instrument? Okay, so can you please explain why did you build the instrument like that? Like the Peltier is between the heatsink, and then why is the fan is over there? Yeah.
Okay, so basically, for the cooling element, it is already in a kit. So normally, if we find the Peltier kit in the industry, we're gonna find the Peltier in the middle, and then it is connected to the heatsink on top of it, and the underneath of the Peltier cooler, and the bottom part of the cooling element is going to be connected with the fan. So it is it will blow air to the to the hot part of the Peltier cooling. Yeah, and then we just like add the um, cooling element underneath the heating element just to make it I don't know, just for the design. Maybe like we can like get the direct contact to the heating element, so that whether if we want to reduce the temperature, the cooling element is directly connected to the heating element.
Okay. Yeah, maybe you can just learn more about the heatsink, yeah. Then the size also, because there are some size for the heat shrink. Yeah. I think that's all. Thank you.
Okay, Jesse and Hanif. Which temperature are you trying to control?
The chamber.
The chamber. So why you put the cooler underneath the heater?
Um.
Uh,
Okay. Yeah, we actually like thought that we will reduce the temperature of the heater,
No,
but
the
I
one
don't know.
the temperature that you want to reduce when it is the time for cooling is the chamber temperature, not the heater.
Okay.
The heater you
Yeah.
just turn off and then you cool the chamber.
Oh yeah.
Yes.
Sorry, sir. Our
Okay.
mistake.
Yeah, please revise it for your first milestone report. Okay, and explain more also, which you with the point that you still miss in the presentation is the algorithm of the control.
Oh yeah.
Yeah,
Oh,
which will form your software. How are you going to control that? Which when to turn on the cooling fan and the Peltier, when to turn on the heater, and how to maintain them? Is it like group 2, yeah, if I'm not mistaken, group 2 or group 4? Group 2, yeah, using on-off algorithm, or you want to use other different control algorithm?
Okay. We actually
Yeah.
gonna use on-off
On-off,
algorithm.
okay.
Yep.
On-off is the simplest, yeah,
yeah.
although not
Yes.
as accurate. You could then, how if it is on-off, how are you going to change that into regulating signal? Is it in the form of, you could use on-off just like, what do you call it, pulse width modulation, PWM, to the heater, or just on-off, like that. Pulse width means by timing the duration, the period of the pulse. You change from long period to shorter period, for example, or just analog, analog on and off, something like that. Yeah, each has their own advantages, disadvantages.
Okay, okay, sir.
So for next milestone, please explain your choosing also, why you choose this and that. But
Sir,
I'm,
can I
yeah,
can I ask a question?
yes,
I think the temperature sensor, it is waterproof, yeah. So if we should it be included in the sample, or it is
yeah,
just like
the temperature sensor itself is waterproof, but the connection is not.
Oh yeah, the
oh yeah.
electricity
The
current.
terminals, if you put it all inside the chamber, it will be short circuited. So you have to have certain kind of water insulation, but still can still transmit heat between the water in the chamber and to the temperature sensor, to the thermistor. Yeah,
Okay.
but I'm quite well entertained by your presentation. It's quite well made presentation. Thank you. So I give you high mark, and the content is good, even though that those minor points, yeah, only you maybe you didn't give a well thought on that. Thank you, Group
Okay.
6, yeah, Hanif and JC. So next presentation will be the last presentation for today from Group 3, Dave and Dimas.
Thank you, sir. Thank you, Kak.
Thank you, JC.
Thank you.
So Dave and Dimas, please turn on your video and you may share your screen.
So I'm going to start.
Yes.
Good afternoon, Pak Dedi, Kak Devita, and everyone. We are from Group 3, which consists of me and Dimas, and we are going to presentate about our final project, which is thermal regulation in a PCR chamber. So first, we will start with the theoretical overview. Now, PCR stands for polymerase chain reaction, where polymerase is actually an enzyme which makes polymers of other molecules, which in this case is DNA. And chain reaction is a type of reaction which which progress in an exponential way. So it will produce product exponentially.
So PCR or polymerase chain reaction is a technique used to make multiple copies of a segment DNA of interest, generating a large amount of copies from a small initial sample.
Okay, So next is PCR usage in diagnosing viral infection. In this case, is the COVID-19. So first, sample will be taken from the patient's nose and then will be put into the tube, which contains important ingredient, and then it will be put into the PCR chamber machine, and billions of copies of the DNA will be produced and can be analyzed later on.
So the important key ingredients of PCR is first we have the template DNA, which is DNA we will want to amplify, and we have the primer, which is the short sequence of nucleotides um, which provide a starting point and select the exact point of DNA of which to be amplified. And then we have the DNA polymerase, which is the enzyme that makes new strand for DNA using existing strand as templates, and nucleotides, which is the basic building blocks for DNA synthesis.
Then next is the thermocycle process, which will be our project. First, the two-strand DNA will undergo denaturation at 95 degrees Celsius to separate the two strands of the target DNA. And then we will go to the annealing process at 55 to 65 degrees Celsius, which letting the primers to bind with the target sequence on a single strand of DNA. And then we will move to the extension, letting the polymerase enzyme to expand the primers and synthesis a new DNA. And so it will go on and go on until the desired cycle reach.
Here are our project plan. And here the list of material we estimate needed to make the PCR. First, we have the sample, which is water. Then we have the chamber, which will collaborate with the first semester student. Then we have the Arduino Uno, which will supply 5 volts and also act as the microcontroller. Then we have the breadboard to connect all the components and to also make it tidier. Jumper wire to connect all the components. The heater to warm to warm it. Then we have the 5-volt relay, which will be used for the heater and the Peltier to control them as a switch. Then we also need a thermistor to accept the temperature input and a Peltier to decrease the chamber temperature.
Then we will also use heatsink for the Peltier to spread the heat so that the cooling side can work properly. And then we use LCD to show the temperature reading, and also 330 ohm resistor is actually used for the LCD to decrease the current flowing to it. And then we use potentiometer. Potentiometer is an adjustable resistor. We use it for it to adjust the saturation of the LCD. And then last is the adapter 12 volt to power the Peltier and also the heater.
Here are the rough circuit schematic of our CPR. We divide it into three parts. First, the top part, the middle part, and the bottom part. Here we have the Arduino, which will supply the 5 volt into the breadboard, which also acts as a microcontroller to control the output and input signal. And for the top part, we connect the relay, which will act as a switch to turn on the Peltier cooling, which will be connected to the PCR chamber.
Next, we do the same thing, but now is for the heater wire. So we connect the breadboard to the 5 volt relay, and so it will turn off and turn on the heater wire so that we can control it using the Arduino microcontroller, and so it will produce heat. And also we want to able to get the input signal from the thermistor using the thermistor, and so it will be read later on by the microcontroller. And also we want to show the temperature reading in LCD.
Here are the Thermostable Algorithm. First, we want to increase the temperature and delaying
it for some specific minutes to undergo the denaturation process at 95 degrees Celsius. We then sustain the temperature at 95 degrees Celsius for a certain period of time by using a loop of turning on and off the heater for some specific delay time. Then we drop the temperature into 55 to 65 degrees Celsius. Then we do the same thing to sustain the temperature. Then this is the annealing process. Then we increase again the temperature, extend the extensions part, then to 72 degrees Celsius, and we do the same thing, the same loop to sustain the temperature.
At this state, the cycle is finished, and then we want to go back to the denaturation process. So we will need to increase from this temperature to 95 degrees Celsius for again denaturation process, and then we will need to do the same thing to sustain the heating process by using the loop, and then we will need to use a big loop to go back to this point, so that we can achieve a desired cycle that we want. And then after we achieve it, we can break from the loop and then turn off the heating and turn on the cooling to bring back the chamber to room temperature. And that is all. Any question?
Okay, thank you, Dave and Dimas. I would like to request Group 5, Osama and Martin, to ask questions to Dave and Dimas. Please turn on the videos. Yeah. Unmute yourself, Martin, Osama, and please ask question.
I have a question, sir.
Yes.
Why do you use the relay in your project?
Okay. So we use relay in our circuit schematic because since the Peltier cooling and also the heater wire can only be powered using a 12-volt power supply, we cannot use Arduino Uno to supply them because Arduino Uno can only supply up to 5 volt. But we want the problem is we want to control the turning on and off based on the algorithm, so that we can have the desired temperature. So yeah, actually the relay acts as a switch for turning on and turning off.
Okay, thank you.
Okay, so do you think using the on and off method to control the voltage is accurate, or you want to use other method?
Yes,
yeah, I think for the first trial, yes, we will use the on and off method.
Yeah, the question is from Martin. Is it accurate enough or not? What do you think about that, Dave and Dimas?
I guess, of course, it won't be really precise. It's turning on and turning off, and when we turn on again, it will also need time for the cooling and also heater to work. So it will really need a lot of trial and error if we really want to make a precise one. So I think we also may try other algorithms.
For example?
Maybe using from the thermistor reading, from the input, we will convert it into an analog signal. And so we'll use when the analog signal receives, for example, sekian volt, then
yeah, what it means is the control algorithm, on-off control algorithm. So you have to search in the internet maybe a better control algorithm, which may require you, for example, to use digital to analog converter of the controller, or maybe a separate chip, yeah, and then use voltage I don't know, voltage regulator or something to control the Peltier cooling as well as the heater. The heater maybe require current control, current something like that, to more sophisticated than relay. Okay, Martin, but do you get or are you satisfied with their answers?
Yes, satisfied, sir.
Okay, Kak Devita, maybe some questions.
Okay, Dave and Dimas, why did you consider of using digital sensor instead of the analog one like LM35?
Using what, Kak?
It's not
Oh.
clear.
Analog input.
I mean for the thermistor.
Oh, we use the analog. Why don't we use analog? Yes, I think we'll use analog instead, so that it's more precise. Later on, we just talked about it.
Okay, so actually the DS18 di berapa 20 ya? This is a digital one, right?
Yes.
It's the digital sensor. Okay. Okay, so next time you want to replace it with the analog one, or just add it with the digital to analog converter?
Maybe we'll try both. Yeah.
Okay, so for next, maybe just explain more about the algorithm of the programming. Yeah.
The flowcharts.
Yeah, the flowchart. Yeah. Make it in a flowchart. Yeah. Have you already learned about flowchart? How to make a flowchart and the
Yes.
shape of the it's you already.
They already learned in first semester introduction to programming, right? In second semester, currently you are learning algorithm and data structure. So you should know about flowchart, right, Dev and Dimas?
Okay. Okay. Well, actually, Catherine and siapa tadi Alicia already made the flowchart, but without the shape of
without the proper shape.
Yeah, without the proper shape. So yeah, well, actually, for each shape have different meaning. Yeah. Okay, so I think that's all.
Thank you, Kak.
Hey, not yet. I haven't asked questions. So what is this box here? So why you draw it here? So what is this box?
Oh, Dimas.
Bread box.
Black box, white box, green box.
Bread box.
White breadboard. Breadboard is for the components, right? Breadboard itself is in the actual implementation, but I mean is in the schematics. You never draw the breadboard, right? You just draw the what circuit you are using, what op-amp, resistor, inductor, capacitor, whatever, and then in the Arduino itself, to which port are you using? Are you using the analog input port? Are you using the digital input port, digital output port, like that? Okay, so a more better representation of the schematic is required here. Understood? So not you don't need to draw breadboard. Breadboard is the actual implementation later. That will be in the Tinkercad thing, but in the schematic you should draw the in the schematic, the symbols, the connections, the networks between the component. So at Arduino, it has how many legs are there, how many ports, and then there is analog input, analog output, and digital input, digital output. Those are what you need to draw then. To which ports the thermistor should be connected to at the Arduino. The LCD should be controlled by what? Should you use a separate LCD board to control the LCD display or what? And how are they controlled by the microcontroller? Yeah, not this kind of a vague board. This is not the standard way to draw in schematic. In Tinkercad, the actual implementation drawing, yes, you may draw that, but in schematic, you have to draw like schematics, yeah, like electrical network schematics.
Yeah.
You get it, Dimas, Dave?
Can I add some maybe?
Yes, Devta.
Yeah, for the schematic, you can use Eagle or Proteus. Yeah, I think those software are better. Are the best
Eagle, yeah,
software.
yes,
Yeah.
yes. Eagle or Proteus.
Just
Even
make
with
this-
Eagle, you can design the PCB if you want to implement your circuit
Yeah.
as PCB
Yeah,
with the
betul.
circuit board.
Yes.
Okay, even though it is not yet the emphasis of this project. Okay, Dave, Dimas, any
Okay,
comment?
yes.
Okay, if not, then that would be all for group.
Three.
Group 3, yeah. Group 3, thank you very much for presenting your work. So, from this presentation, yeah, most of the groups that what you call it, that do project 1 have got it correct. So, even though the details are still missing, but groups that are doing group project 2, thermal regulation and active temperature sensor, many of you still misunderstand the project, what is it all about. Okay, so I do not want passive temperature sensing. That will be too easy for you. No point of keeping it as projects. So I want you to develop a control system for an active temperature sensing. So those groups, do you understand those things? Those who are doing project 2, active temperature sensing, do you get it? From all of you, I think Martin has shown response feedback that he understands. So I'm not sure the rest, the other groups, the other 2 groups. So please, you can ask Martin. He understands what I meant. Okay. So please revise your report. The deadline for the report for this first milestone is Friday night. So you still have about 2 days, 2 nights, 48 hours to revise your concepts, your presentation. Please put the presentation file, also upload the presentation file and other supporting file in the folder that I have given, and upload your report and your PPT to the Google Classroom. Any questions so far? Hello? No questions? No need for OTP?
No questions, sir.
Huh?
They don't need the OTP for the
Oh, OTP, yes, sir.
Yeah. Okay. So OTP for this is use the electrical circuit lab, not the electrical circuit. But electrical circuit 2 laboratory session. Week 12. Week 12. Let's use this session 1 or session, or you can input twice. It's possible. The OTP is 1905. 1905. Okay, I look forward to receiving your reports. And the second milestone today is week 12. So week 14. So in week 14, we will have another presentation. Actually, that is, we will find the other timing, because at week 14 you need also to present your module 4 basically of lab. So please be prepared. So at week 14, I hope we already get some improvement,